Welcome to the Deep Dive. We're here to pull out the key insights from some really cutting-edge science. And today, wow, we're looking at something that feels like it almost flips physics on its head, a real head-scratcher.
It really is fascinating stuff. Our mission today is to explore how scientists over at SLAC National Accelerator Laboratory managed something quite remarkable. They superheated gold, plain old gold, to temperatures people honestly thought were impossible.
Okay.
And we want to unpack, what that actually disproved about physics, and maybe more importantly, why this matters for things like space travel or even nuclear fusion. We're basing this on some new research in Nature, and there's a good piece on Gizmodo discussing it too.
Right. Let's jump straight in then. Superheating gold. Just how hot are we talking, and why is that temperature such a big deal?
Oh, it's genuinely staggering. They push gold to 14 times its normal melting point. Think about that 14 times. We're looking at around 33,740 degrees Fahrenheit. That's what, 18,726 Celsius?
Incredible. How did they even do that without it just vaporizing instantly?
Well, that's the clever part. They used a really fast laser pulse to heat a tiny gold sample. But crucially, they do it in a way that stopped it from expanding, kept it sort of contained. Then, almost immediately, they hit it with extremely bright X-rays from a special setup they have at SLAC, the MEC instrument.
Okay.
And by looking very closely at how those X-rays scattered off the gold atoms, the tiny changes in frequency, they could actually calculate the temperature of the atoms directly. For the first time, really, it was apparently so surprising. One of the lead authors, Thomas White, actually said something like, "Hang on, is this scale right? That number looks really hot, doesn't it?"
Ah, bet. But okay, here's the part that really grabbed me. It wasn't just a high score on the thermometer, right? This actually seemed to break a long-standing physics rule.
Exactly. That's the core of it. For decades, there was this well-accepted model in physical chemistry.
Entropy catastrophe, wasn't it?
That's the one, yeah. And it basically predicted, based on thermodynamics, that you just couldn't heat a structure like gold more than about 3 times its melting point, which for gold is around 1,948 Fahrenheit or 1,064 C. The thinking was, beyond that, the structure would become too disordered. It would essentially, well, blow up. Thermodynamically unstable.
So everyone just accepted that limit. 3 times, that's it.
Pretty much, yeah. It was a foundational concept. But these results, they didn't just nudge past the limit, they absolutely smashed it. 14 times is way, way beyond 3. It strongly suggests that if you can stop the material from expanding, maybe there isn't a fundamental limit to how much you can superheat gold.
Wow. Okay, that's a big shift in thinking. It's like finding out a basic rule just isn't true under certain conditions.
Yeah.
So if this rewrites a rule book, what does it actually mean for us? What are the practical, real-world uses for this new thermometer, as you called it?
Well, I think the implications are quite broad. This new technique essentially gives scientists a reliable way to measure temperature in these incredibly extreme states of matter. Think about trying to understand what's happening inside a star, or on the heat shield of a spacecraft burning through the atmosphere, or inside a fusion reactor.
Places you can't just stick a regular thermometer.
Exactly. Before this, temperature measurements were often indirect. You'd measure something else and infer the temperature, which led to this sort of chicken and egg issue. Was the theory wrong, or was the temperature measurement off? Now, they can measure it directly. Take the National Ignition Facility, for example. They use tiny gold cylinders in their fusion experiments.
Right.
And figuring out the exact temperature inside those cylinders during the experiment has been a really tough, long-standing problem. This technique could potentially solve that. And it's not just gold. They're already using this approach on other materials like silver and iron, so it seems pretty versatile.
Okay, so it's not just a record-breaking temperature feed. It's a fundamental new understanding of how stable matter can be, and it's a practical new tool for exploring these extreme environments.
Precisely. It really opens up new avenues. And maybe, a final thought to leave with everyone listening. If we can now effectively get this kind of X-ray vision deep inside matter under extreme conditions, mapping out exactly what the atoms are doing and how hot they are, well, it makes you wonder, how much more control could we eventually achieve over materials and environments that, until now, we could only really simulate or imagine exploring? What new possibilities does that unlock?